You probably remember, I hope, from the first semester, your first introduction to acids and bases was in nomenclature. We learned how to name acids. And at that point, all you needed to know was that the acid formula started with a hydrogen, at least one, maybe two, maybe three. Now we're going to, and we've touched on acids and bases occasionally, the chapters, but now we're going to get more intense because there's a great many reactions that occur in nature, even in our bodies, are acid base. And for those who are going to take organic chemistry, that's a huge part of organic too, is understanding acids and bases. In fact, acids and bases in terms of not just movement of hydrogens, but movement of electron pairs. And we'll get to that one eventually. But the first attempt at defining what an acid and a base were came from Arrhenius, Svante Arrhenius. You've seen that name before, I'm sure. Maybe kinetics. I think we had Arrhenius in that one. His definition said that acids produce hydrogens in aqueous solution, and bases produce hydroxyls in aqueous solution. He didn't just say they produced them, they came from the molecule itself. So an example here would be HCl. Right? It would ionize and produce a hydrogen ion and a chloride ion. Or a base, like sodium hydroxide, would dissociate into sodium ions and hydroxyl ions. And that worked fine for most acid-base reactions. And quantifying the concentration of either one would allow you to define the strength of your acid and base solution. Now, we're going to talk about strength in just a minute in other terms. But there were some solutions that were obviously basic, but they didn't have hydroxyls in their molecules. And best example of that is when you dissolve ammonia in water, it produces a basic solution. There's no hydroxyl in that molecule. So we had to change our thinking a little bit. And what we did, or what Bronsted and Lowry did independently, was treat water as a reactant. If you do that, and you think in terms of proton movement, or hydrogen ion movement, then we can get a hydrogen ion transferring from this water molecule to that ammonia and gives us the ammonium ion. And what's left over from water, take one hydrogen away, you get a hydroxyl. So that's where Bronsted and Lowry come in. Their definition focused solely on proton movement. They didn't care about hydroxyls. I mean, hydroxyls are there, yeah. But as far as defining what an acid and a base was, they simply said that an acid is a proton, or I say proton interchangeably with hydrogen ions because most of them are protons once they lose their electron. There are a few, like deuterium and tritium, that have an extra neutron. But for all intents and purposes, I'm talking about a proton here. Is a proton donor. Any acid that donates a proton. Any one that accepts is a base. And that covers all of the Arrhenius acids and bases and encompasses most of the others. Now we're going to get to another one here toward the end. I think it's this chapter that takes all of these and expands the universe even further. But I'm not going to hit you with that one yet. Let's talk about these first. So once we got Bronsted and Lowry's definition in mind, then we could treat any acid or any base in terms of its reaction with water. So if we said, we've got an example here where this is an acid, this is the acid, right? And this is the base, is the proton acceptor. And you can look at, say this one, right? We know, experimental proof, that protons do not exist by themselves in aqueous solution, or in any solution for that matter. They're always transferred from one place to another. They don't exist as free-floating hydrogen ions. Now, we sometimes treat them that way mathematically because it's more convenient. So I just want you to understand that when you put that in aqueous solution, what you get is this proton transferring over there, and we get this chloride ion by itself, right? This hydrogen left its electron behind and transferred over here and produced a new polyatomic ion called the hydronium ion. And if you go back and look at your list of polyatomic ions, well, hydronium may not be in that list, but it is a polyatomic. This is the way, if hydrogen is not attached to anything else, it will always be attached to a water molecule and produce the hydronium. So we can speak, and this, of course, was the acid. Now water has become the base. Over there, it's an acid. Over here, it's a base by the Bronsted-Lowry definition. And that's the one we're going to use most of the time. This is just a little animation for the molecule on the left is ammonia. And then you got your water molecule on the right. And there's kind of a tug of war there. You can also get, if you have pure water, you can also get this type of reaction. And one of those waters, we're just going to arbitrarily say this one's the acid. This one's the base. So we transfer a proton. We're left behind with this, and it transfers the proton, and we end up with that. Okay? That's an acid, that's a base. And this is just pure water. Now, this doesn't happen to a great extent, right? The equilibrium is largely this side, but it does happen. And it always happens in any aqueous solution. No matter what else is going on, this goes on as well. Definitions. Let's see. Yeah, I can use this one. This acid loses a proton and produces a base that we call the conjugate base. This is true for any acid. When it loses its proton, it produces a conjugate base as a product. And this is the conjugate acid. Of this space. The only difference between this one and this one is lost a proton. Between this one and this one, gained a proton. Okay, and whenever we talk about acid-base reactions of any kind, well, let's focus on acids. It's one proton at a time. If you've got more than one proton available, like in sulfuric acid, it'll transfer one proton and we can treat that as an equilibrium situation. And then what's left over, HSO4 minus, right? We can treat that when it loses its proton as a separate reaction. So each proton movement produces its own equilibrium equation. Let's see. All right. Now, talking about strength. If you're an agent of the government for the EPA or OSHA, you might have a different idea of what strength is. They speak in terms of corrosivity, how corrosive is a solution. So you can produce an extremely corrosive solution out of a bottle of glacial acetic acid, which is 100% acetic. But it's only corrosive because there's lots of acetic acid there. The acetic acid itself is weak in chemical terms because its equilibrium is back here predominantly. Right? So we would end up with this conjugate base and this conjugate acid. So this one's weak simply because the equilibrium lies far to the left. Right? It does not ionize to any significant extent. And we can quantify it, right? It has a Ka associated with it, right? An equilibrium constant, right? We just say C2H3O2 minus, and then hydronium, and then all over the undissociated acid, right? We don't include that because it's pure liquid, right? So we get these equilibrium expressions for, they're especially useful for weak acids because you do have a significant amount, a measurable amount of that. If it were a strong acid, it would essentially all be over here. And then you'd have what would be down here, basically zero, right? So our Ka would be infinity. That doesn't have any meaning. But this is a weak acid. Strong acid is one that completely dissociates, lies far to the right. Now, the other concept, when you have an acid producing a conjugate base, they're always related in terms of strength. This is a weak acid. This will be a strong conjugate base. Now, what do we mean by that? Well, the weak acid we've defined, right? It doesn't give up very many of its protons, which means it really wants to hold on to them. It has a strong attraction for its protons. So that means if we get to this side with a conjugate base, it still wants to hold on to protons, which makes it a strong acceptor. Right? That's what we mean by weak and strong. This one doesn't want to give up its protons. This one's going to find protons somewhere. So if you put this ion in solution, independent of that, say it's a sodium acetate or ammonium acetate, you put that in solution, then it's going to dissociate into its ions. This is going to go looking for protons. And the most plentiful source is water. So it's going to snatch protons from the water like crazy and produce a lot of this and leave behind what? If it takes a proton from water, it leaves behind hydroxyls, which makes the solution basic. So weak acid, strong conjugate base, strong acid, weak conjugate base. So if we have this pair like that, this would be the strong acid, this would be the weak conjugate base, acid-base pair. Okay. This is the author's idea of an explanation. I don't see much use in it myself. I don't know why I keep it here. I'm too lazy to get rid of it, I guess. Okay. So that's another reason that we hit equilibrium first before we get acids and bases. All right, this just summarizes everything that we've talked about so far. So we're not going to hit that one. That illustration that I gave you of water as an acid and water as a base is common to other molecules also. If we have, the bottom one is anhydrous ammonia, right? And if you're a corn farmer, the most economical way, if you have the equipment to nitrogen fertilize your crop, and corn is a massive sink for nitrogen. The best way to fertilize your corn is with anhydrous ammonia. That is pure 100% ammonia in a stainless steel tank. All of your fittings have to be stainless steel, right? Because it'll eat anything up that's not. And you force it under pressure through stainless steel knives that's cut through the soil. They're about that deep to get it into the moisture. And once it gets into the moisture, of course, it reacts with water and produces a solution, a very basic solution that essentially kills everything in a zone like that wide. So once it's in there, you have to let the soil recover and microorganisms and roots reinvade the area as it spreads and weakens. But this concept of proton transfer in this pure ammonia solution, if this is our acid, this would be the base, and we just transfer a proton over to that side, and we end up with NH2 minus, oops, not aqueous. Can't say that. I don't know what you say, liquid maybe. And then ammonium. So you get this autoionization. In other words, auto means self. So that's the only thing in there, so it has to be self. You can't react with anything else but itself. Now this autoionization comes by a couple of other names. Amphoteric is one of them. Water is amphoteric, which means it can behave. Ampho means both in Greek. Ampho, it can behave as an acid or a base. So in the case of water, it does just that. And we get two waters yield what? Let's see if this is our acid. Then we transfer and we get hydroxyl and hydrogen ions. Well, actually we get hydronium ions. But for calculation purposes, we can use this expression. It works just the same. And it's a little easier to deal with than writing H3O plus every time. So when we write the equilibrium expression for this one, and this one W is reserved for water, then we don't use this one or that one because they're pure liquids. So all we have are these two components. And that is equal to 1 times 10 to the minus 14. okay, at 25 degrees. All right, so where are we headed with this? Well, now we're going to discuss whether the solution is acidic, basic, or neutral. Of course, if it's pure water, it's got to be neutral. And this concentration is equal to that concentration for one very good reason, because they both came from the same source, right? So if you get one of these, you got to get one of those. You have no other choice, which means these are equal. And if they're equal, the solution is neutral. Now, if we introduce excess hydrogen ions, like we have this water and we put hydrochloric acid in it, right? The chloride ion would be a spectator and the hydrogen ion would participate in this reaction. The reason chloride ions don't participate is why? Conjugate base of a strong acid is a weak base. So chlorides don't care about protons at all. So we introduce the proton on this side and it shifts slightly this direction, right? For equilibrium purposes, but it doesn't use all of them up. There's still excess hydrogen ions left over here, right? So in that case, when hydrogen ion now exceeds hydroxyl ion, we have an acidic solution. Okay? And vice versa. If we put hydroxyls in here, we get a slight shift this way, but we still have excess hydroxyls left over, which makes it basic. All right, now we're going to quantify that. We talked about this already. There's the equilibrium expression for, oh no, we didn't. In general, for acids, yeah, I did introduce that one, right? With acetic acid. This is the general expression for the acid dissociation. Actually, it's acid ionization. There's a distinction between the two terms. Acids are covalent, right? This is a covalent compound, which means if the hydrogen leaves, we have to describe it as an ionization. So if we end up with this and this, that's ionization because the ion wasn't there before, right? It was covalently bound to that, whatever A is. But if we have a base, bases are, well, the hydroxyl versions of bases, like sodium hydroxide, is already ions, sodium and hydroxyl ions. So this one, when it breaks up, we call that dissociation. I know it seems kind of picky, right? But it's the truth. Okay, so if the equilibrium lies to the right with a Ka, that means you will have a relatively large K value. If it lies to the left, as written in these terms, then the K will be small, much less than 1. All right. Let's make some room here. Fresh rag works better. I throw away those old ones. So for this example where we have an acid, a generic acid, HA, we put it in solution, it reacts with water and produces the hydronium ion and the conjugate base of the acid. If water is a better base than A minus, that is, water is more attracted to hydrogen ions than they are to the conjugate base, then which one dominates? If water is a better base, then it wants to accept protons. So I would think the equilibrium would be favoring products. Water would accept a proton from the acid and shift to the right. Does this mean HA is a strong or a weak acid? Well, if water is a better base than A minus, the competition is from this side to that side. So which one attracts hydrogens better? Well, if water attracts hydrogen better, I would think HA would be a strong acid, because A minus doesn't want protons. Okay? Think about it a minute. So the Ka would be greater than 1, because that water molecule is grabbing protons from the acid and sending the equilibrium to the right. Okay, say we have 1 molar solution of hydrochloric acid, and we want to put these in order from strongest to weakest base. So the reaction, let's see, what do we have? We've got water, we've got A minus, and we got Cl minus. Okay. A minus from a weak acid. All right, we're comparing 2 reactions here. If we got this reaction plus water, and it produces A minus plus hydronium, and then we got HCl plus water, and it produces Cl minus plus the hydronium. So it says that HA is a weak acid. So this Ka should be much less than 1. It prefers this side. This one is going to be a Ka of essentially infinity. It wants to go all the way that direction. Right? So that means if this is a strong acid, that means this is a weak base, right? If this is a weak acid, this is a strong base. Okay. Now, if we're going to compare those to water, water is a relatively weak base. We know that because Kw equals 10 to the minus 14th. Yeah, water's a weak base. It really doesn't want to accept a proton. So from strongest to weakest, I would say the weakest base actually is this one right here. So this is the weakest base. Now we have to decide between this one and water, which one is the stronger base. I would think that water would be the strongest base, and A minus would be in the middle. Oh, strongest to weakest. Wait a minute. I got messed up. How good is chloride as a base? Oh, it's going to leave it up to the instructor to talk about it. Okay. So for strongest to weakest base. Oh, I'm sorry. Oh, no, that's not right. That's the weakest base. And it should have been on this side, right? Strongest to weakest. So the strongest base would be, well, I was a toss-up between this one and this one. But the weakest base, of course, is going to be that one. So they're saying that A minus is a stronger base than water. Oh, yeah, it is. Yeah. Okay. Yeah, I'll agree with that. I won't. I have a problem with this one. Yeah. It could go either way, depending on what the Ka is for that weak acid. We'll hit ones like that again later. We're just trying to get our feet wet right now. If we were trying to solve the world's crises, then we'd spend more time on it. Okay, so consider a solution of Na, like we did before, sodium acetate. This would be sodium salt of whatever. And A minus is the anion from a weak acid. Well, when you put them in solution, right, when that goes into solution, it breaks up into sodium ions and A minus ions in aqueous solution. So this is like a spectator. Then you have this one, which is from A minus is the conjugate base of a weak acid. So this is a strong base. And it's in solution. And the only thing it has available to it is water molecules. Okay. So it's going to be very aggressive at removing hydrogen from that water molecule. And get this right here. Okay. So that means this is a strong base. This is the weak acid, right? So it doesn't want to give those hydrogens back. It's taking hydrogens from here. So this equilibrium is dominantly to the right. No. I did that because the slide, this came from the publisher and they got it wrong. They probably turned it over to a graduate student or assistant and they just flubbed it. The equilibrium lies to the right. Okay. Is the value for KB greater than or less than 1? All right. We didn't talk about KB. How would we write KB? Well, if this is a base and we put it in water, then we can write an equilibrium expression for that base, right? We have HA, concentration, OH minus, and A minus, because water is a pure liquid. So this is the KB, right? As opposed to the Ka. What would the Ka look like? Right? It has that, and this, right? So they're nothing like each other. They're related. We're going to talk about that in a minute. But this is the KB for that base. It has to be this way because the base is looking for protons. And if we write it this way, then we can say, what's the equilibrium expression? Well, if it lies far to the right, this is a strong base, then this KB is going to be greater than 1. And we're going to be far to the right. No, that's wrong. It's greater than 1. The KB for the conjugate base of a weak acid, the KB is greater than 1. In some cases, much, much greater than 1. Okay. Let's see. Well, it means that A minus is a strong base. Okay. All right. So let's see how much more trouble I can get into. Acetic acid and hydrocyanic acid, right? No oxygen, so we say hydro, are both weak acids. Acetic acid is stronger acid than HCN. Okay, so we have C2H3O2, and we have HC. Oops, of course I have CN. Right, and this produces conjugate base and the hydronium ion. And this produces the conjugate base and also a hydronium ion. These are two separate solutions. Okay, arrange these bases from weakest to strongest. Okay, so what do we have here? We got water. Water as a base. Chloride as a base. They're slipping that one in on us. If we say this and that, produce chloride plus H3O plus. Then we can talk about the chloride. And then cyanide ion and acetate ion. Okay, strength of the base. Well, which one is the, if we want to say what's the weakest base here, we look for the strongest acid. Right? There's the strongest acid. So the weakest base is from weakest to strongest, chloride. Right? That's the weakest. Okay. The strongest base is going to be conjugate base of the weakest acid. So we know that we've been told that this is a weaker acid than this one. So that means cyanide should be the strongest conjugate base. Okay. All right, so it's a toss-up now between acetate and water. Which one is the strongest base? Well, if we don't know what the Ka is for this one, then we can't talk about that in terms of its equilibrium constant. So we have to sort of generalize. My guess is that they think that this is going to be a stronger conjugate base than water. But I would disagree. Oh, it didn't give us an answer. Oh, there's the answer. Yeah, they're saying that this one is a stronger conjugate base than water. And the only way to prove it is to calculate the Kb for this one versus this one. So I'm going to let it go at that for now. Maybe they are talking about it. Okay. Kw is 1 times 10 to the minus 14. Ka for the acid is 10 to the minus 5. We got this one covered. HCl is a strong acid, so this is the weakest base. This is the HCN is the weakest acid, so it's the strongest base. And then we have a comparison between these two. Right? Did it give us? Yeah, 10 to the minus 5. So this is Ka equals about 10 to the minus 5. And H2O plus H2O plus, and this Kw equals 10 to the minus 14. Okay, this is 10 to the minus 10. This is 10 to the minus 14. And this is 10 to the minus 5. I'm gonna have to disagree with him. Well, no. Okay, okay. I see the reasoning now. We're talking about water. This is, if we focus on that and try to compare, it's like apples and oranges. This would be a valid argument for hydroxyl, right? But we're talking about this part of the molecule. I mean, this part of the reaction. So it doesn't want to go that far too much. So it is a weaker base than this one because it wants to be back here by a significant amount. Okay, so I'll give that to them if that makes any sense. Yeah, I didn't think it would. What we're trying to get to now is to understand, in a sense, an equilibrium sense, what happens when you get two acids reacting or some competition for protons. That's what we're after. Because our discussion this far has been really, really very simple and not very common in the real world. Right? We can reproduce these things in the laboratory, but in the real world, you've got competition among various acids for protons, for giving up protons and bases for accepting them. So here's our example. We try to intuitively decide whether the K for this reaction is equal to 1, less than 1, or greater than 1. So we've got HCN, right? And we've got fluoride. I'm not writing aqueous in here. It's just too much trouble. So this would be CN minus and HF. Okay, so the proton is transferred from here to here. Acid transfers to base, produces a conjugate base and a conjugate acid. All right, now we know that the Ka for HCN is 6.2 times 10 to the minus 10. Ka for HCN equals 6.2 times 10 to the minus 10, which would be represented by HCN here, and then our simplified version there, CN minus. And then Ka for HF is equal to 7.2 times 10 to the minus 4. Times 10 to the minus 4. And this would be also hydrogen ions, but F minus over HF. So that's given information. What we want to know is what's the K for this combination? Intuitively first, greater than 1, less than 1. So this tells us that HCN is a weaker acid, so it makes a stronger base compared to F minus. So this is a strong base. In fact, stronger than F minus, right? Because this one is a larger, this is a stronger acid. Just compare those two. This is a stronger acid, which means it prefers to give up protons from this side. And this prefers to accept them from this side. So this is going to produce an equilibrium that's largely this direction. It's going to be over here, which means what? Less than 1 is. Yeah. Oh, this one does have a discussion. Okay. Yeah. Driven toward reactions. The Ka, actually, it's not Ka for the overall reaction. It's just KEQ. Right? Because Ka is going this direction and Ka is going that direction. So it's like intuitively they cancel each other out. So it's a KEQ of a reaction between this acid and that base. This is an acid-base reaction. Okay. Now we're going to learn how to calculate Kb when we know Ka. Right. So here's our generic acid dissociation, and we're using protons here instead of hydroniums just for simplicity's sake. That's our expression for Ka. If we take the conjugate base and react it with water, then we get this expression for the Kb. Okay? So how are they related? Well, if we add them together, what do we get? Well, notice that the A minus on the right cancels the A minus on the left. Right? We're talking Hess's law. So the A minuses cancel out. The HAs cancel. HAs on one side for one and on the right side for the other. They cancel. And what do we get left? Well, got to go through my animations here. What we have left is water dissociation. And its value is Kw, H plus times OH minus. Okay? So if we want to solve for Kb, we find out Kb based upon Ka, then we rearrange the equation to solve for Kb, and we end up with Kw over Ka. So you can calculate Kb from Ka, the Kb for the conjugate base, right? We could calculate Kb for this one. Kb for this one would simply be 1 times 10 to the minus 14 divided by 6.2 times 10 to the minus 10. Okay? Kw divided by Ka would give you the Kb for this conjugate base.
And that's always Kw?
Yes. Yes. Right. It's like a constant. Yeah, so if you want to see what happens to the cyanide ion in solution like sodium cyanide, you add it to water. You get cyanide reacting with water, and the equilibrium constant for that reaction is this, whatever that happens to be. I can't do 1 divided by 6.2 in my head. And if you know Kb, you can calculate Ka. It's just they swap places. Right? Ka comes over here, Kb is over there. If you know what Kb is, then you can calculate Ka for the conjugate acid. Yeah, the temptation is to say that Ka is the inverse of Kb, and it's not. Now, we do use inverses occasionally, but we have to justify them. Let's see. Oops. Better not erase anymore. I might be coming up with that same reaction. What are we going to do with it this time? Okay. Calculate the value of K for the reaction. Okay. We got these overall reactions for HCN 6.2, wasn't it? Yeah. And I erased this one already.
Was it the 7.2?
7.2?
Yeah.
Times 10 to the minus 4, is it?
Yeah.
Yeah. And this is the Ka for that one. This is Ka for this one. Okay. So if we break this reaction in half, break it up as if we were going reverse Hess. Right. There are two acid reactions. The HCN we leave alone because HCN is going to Cn minus. That's correct. But the HF is going the other direction. We're actually going F minus to HF. So we need to invert the reaction, right? And when you take the inverse of a reaction, the K value is inverted. All right, we studied that in chapter 13. Now we can add them back together. Okay, so we got these two reactions. Add the reaction together and we get, and when we calculate the K, then we take the K for this one and the inverse of the K for that one and multiply them. And that gives us the K for the reaction. So 8.6 times 10 to the minus 7 is the K for this reaction. So that's a case where we do want to invert a reaction. Question?
Yeah, maybe. Why doesn't we take the inverse of the 7.2 and not the other one?
Okay. Because, let's go back. Because this reaction has HCN on the correct side. So we leave it alone.
Okay.
But this one, we know what HF to F minus is. We need to know what F minus to HF is. So that's why we took the inverse. Then when we add them back together, the next slide shows you that when you add them back together, you got these hydrogens in there, right? Because that's the way the dissociation works. Ionization works. But the H's cancel. And that leaves us with the reaction that we want. And then all we have to do is multiply the K's. All right, pH. Everybody's heard of pH, right? Yeah. What I want to do is treat pH as just another formula. Right? This was developed by, did I put the history in here? No, I didn't. Developed by a Swede. I think his name's Sorensen. He was a researcher working with hydrogen ion concentrations, and I think he was working with biological systems. And he wanted to not have to deal with scientific notation, all these negative powers of 10, right? Because that's what you get with weak acids. So he came up with this transform. It's a logarithmic transform that he called pH. And this is the same as the hydronium concentration. But it's just easier to write this way. And it makes more sense when we're trying to equate this with that. So if he has something like, let's just make something up. Say he has hydrogen ion concentrations of 10 to the minus 2, 1 times 10 to the minus 2. And so if you take the log of that, you can get rid of the exponent. Take the common log, base 10. So the base 10 common log of this is equal to minus 2, correct? Right? But he didn't like negatives either. So I said, okay, I'll just put a negative in front of this. That gets rid of it. So now he's got a system where he can express the hydrogen ion concentration in a logarithmic scale that is easier to handle than scientific notation. And this he called pH. Little p, big H. Anything else is wrong. Big P, big H is wrong. Big P, little h is wrong. In fact, in organic chemistry, big P, little h is phenol. So there it is. So what we learned from this is that since we took the log of that calculation, if we say we want to do the same thing for 10 to the minus 3, right? Well, that's going to be negative log of this value, which is 3. Right? So we've increased by 1 unit, but we've decreased the hydrogen ion concentration by a factor of 10. We call that an order of magnitude. 1 order of magnitude decrease in hydrogen ion concentration increases the pH by 1 unit. Okay? That's simply because it's a logarithmic scale. What we find out is if we use this system, that right here in the middle where we say neutral would be the negative log of what? 10 to the minus 7. Right? Because when we say Kw equals 1 times 10 to the minus 14, which is equal to H plus times OH minus. How did we get there? Well, if it's neutral, they have to be exactly the same value, don't they? If it's neutral. And the way you get to 10 to the minus 14 is to multiply 10 to the minus 7 times 10 to the minus 7. Right? So that means this concentration, this hydrogen ion concentration, is 7 on the pH scale. That's where pH 7 became neutral. Okay? If we go, hydrogen ion concentration is going up, right? Increase. Say it goes to 10 to the minus 5. They were right here, say 10 to the minus 5. Okay, negative log of 10 to the minus 5 is 5. So the smaller the value, the more acidic the solution. And you've got 2 things working here is the logarithmic scale that changes this to a digit and the negative, which gets rid of the negative. So that's why it goes from 7 to 5 more acidic. And we typically don't go much beyond pH 1 for acidity. You can go, right? It's simply math. So let's say we had a 10 molar HCl, right? That's a strong acid, so it's going to produce 10 molar concentration. Negative log of 10 molar is what? Minus 1, isn't it? Because it's 10 to the 1 power. The log of 10 to the base 10 is this 1 and then a negative. So this is a valid calculation for pH, only it doesn't tell us much. If we go the other direction, right, we can go up to, in the neighborhood of 14 is usually where we stop. So if we went, say, negative log of 10 to the minus 9. Right, now we've got a smaller amount of hydrogen ion concentration here. 10 to the minus 9 means what? If this is 10 to the minus 9, what does that have to be? 10 to the minus 5. Right? So 10 to the minus 9 gives us a pH of 9. And a hydrogen ion concentration of, 10 to the minus 9 gives us a pH of 9, but the hydroxyl is 10 to the minus 5. Okay. So the bigger the pH past 7, the more basic. All right. And there's just some different things that on a pH scale. Like milk is very slightly acidic. Black coffee is a bit more. Vinegar is about 3. Stomach acid depends on whether if you eat a heavy Italian meal with lots of tomatoes in it, it'll be down around 1. but normally your stomach pH is about 2. And then battery acid is around 1. Blood pH, anybody take anatomy and phys in here? What's the normal buffered pH of blood? Blood plasma, actually. 7.35 to 7.45 pH. Very narrow range, right? If you go lower than that, you know, you're in acidosis. You go higher than that, you're in alkalosis. And those are unhealthy situations and sometimes life-threatening. But that pH is maintained by a buffer system, and we haven't talked about buffers yet, but we will. Okay. Let's see. Let's try an example here. Let's see. Yeah, I'll leave that. So that was Sorensen's contribution. It was fairly widely accepted very soon. It just solved so many problems. If we want to calculate the pH of, if we know the hydrogen ion concentration at equilibrium, that's what that means, is 1 times 10 to the minus 4. That's a fairly simple calculation. And the minus 4. Why can I say that? Because if I say, let's do it this way, just to prove, times 10 to the minus 4. Like that. Okay, what do you do when you have the log of a product? The log of A times B is the same as the log of A plus the log of B. Correct? That's a rule, logarithmic rule. Well, what power of 10 gives you 1? 0. Right? So this one goes out because it's equal to 0. So that we just have to deal with this side. Well, 10 to the minus 4 natural log, common log is minus 4 times minus 4 is 4. I didn't want to skip a step. Oh, I think I got a slide on it, but here we'll illustrate the point. If you have, let's see. Yeah. You have 2 significant figures in your coefficient right here. That translates through logarithmic transform into 2 decimal points in your answer. So this is actually that. 2 significant figures, 2 decimal points. If we went backwards, then 2 decimal points means 2 significant figures in your coefficient. All right, how about this one? I'll do B over here. If we have 0.040 molar hydroxyl ions, we can't calculate pH yet because we don't know what the hydrogen ion concentration is. But we do know this. We know that 1 times 10 to the minus 14 equals times hydroxyl, 0.040. Okay? So we can calculate the hydrogen ion concentration based on that reaction. This is Kw equals that expression. This is OH. Right? So we just solve for this one. We say 1 times 10 to the minus 14 divided by, what's that? 4 times 10 to the minus 2. Right? Okay. So this is 0.25 times 10 to the minus 12 and 2.5 times 10 to the minus 13. Now we can take the negative log of this. And you follow me so far? Okay, what'd you get?
Oh, hold on. I put it in wrong.
Okay. And we have two significant figures here, so we're gonna have 2 decimal points in our answer.
12.60.
Mm-hmm. Go. All right. Now, the reason we showed you this way, right? This is the long, hard way. I'm going to show you a shortcut in a minute. It makes it go a lot quicker. But first, let's say we know what the pH is and we want to calculate what the hydrogen ion concentration is. Because equilibrium expressions don't work in pH. They work in actual molar values. So we're going to take 5.85 pH and convert that to hydrogen ion concentration. So if pH equals 5.85, you just say, all right, what is that equal to in Sorensen's expression? Negative log of the hydrogen ion concentration. Okay, so what we want to do is get that negative over here, because the negative or in this region spoils the calculation. So we move the negative is log of hydrogen ion concentrations. Okay, what does a logarithm mean? There's the base 10. What it means is this is the power of 10 that equals that, right? So we can write it this way. Power of 10 that equals that. And your calculator, wherever you have log, shift it and it should be 10 to the x. So with 5.85, I'm going to change the sign and then hit 10 to the x. And this is 1.4, let's see, 2 decimals, 2 significant figures, times 10 to the minus 6 molar. Okay. Oh, I did an animation for this one. All right. What I just did was calculate the anti-log. So H plus equals the anti-log base 10 of negative 5.85. Means the same thing. In case you ever see anti-log, then you know what you're dealing with. Okay. All right. Now for the shortcut. Since Sorensen's expression is purely a mathematical transform, we can do that same thing for other concentrations. So it seems logical that we would do it for hydroxyl ion concentration, negative log. And we use this same naming convention, POH. That's POH. Okay. Now, since we said POH here, and we said pH here, if we go back to, and we can also do this one, might as well show you this one. You can do it with K values too. Equals P KW. We go back to the expression for water dissociation, and we say KW equals H plus OH minus, and at 25 degrees, that's 1 times 10 to the minus 14. We can take a negative log of that entire expression. And we just say negative log of the whole thing. So the negative log of this side would be PKW. Negative log of this one would be pH. negative log of that one would be POH. And the negative log of this one would be 14. Okay. Now, what goes in here? When you take the log of a product, you get the log of one term plus the log of the second term. So this is a plus. Okay. There we go. So that says pKw equals pH plus POH equals 14. All right, now, if we want to calculate the POH for this hydrogen ion concentration, 1 times 10 to the minus 4 molar, that's messy, minus 4 molar. This is hydrogen ion concentration. We want the POH. All we have to do is take the negative log of that, which is equal to 4, and then plug it into this formula. Right? So POH is equal to 14 minus pH. 14 minus 4 is 10. POH. Okay. And 0.040. Let's see. Let's move up here. For B, if we want to find the POH of 0.040, right? That would be POH. And POH would be equal to, better use a calculator. Is that right? Yeah, round it up. Got one?
1.40.
Uh-huh. All right. So if we go back and say, all right, what's the pH of that solution? Like from a previous problem, we had the POH and we went the long way around. Now that we know POH, then pH is equal to 14 minus 1.40, which is 12.60, right? So we got the POH of the solution, which is a small negative number, and the smaller number means higher value. So pH, this is a basic solution. We also know that pH, when it's greater than 7, is basic. So we got agreement there. What's the OH minus for this solution? We calculated POH before, didn't we? Or did we calculate pH? What's the OH minus? Okay, we calculated, oops. All right, that's okay, we can do it again. All right, we want hydrogen ion concentration of this solution is the anti-log of negative 5.85, right? And so that's, we do that one again. Change the sign and do that one. 1.4, yeah, 1.4 times 10 to the minus 6 is that one. But if we want POH, oh, we don't need that. POH equals 14 minus 5.85. Have to read the problem occasionally. This is 8.15 is POH. Right? Oh, it asks for hydrogen ion, hydroxyl ion concentration. Okay, so Hydroxyl, it's simple now. We just take the anti-log, or 10 to the minus 8.15. Change the sign, go there. All right, this is 7.1 times 10 to the minus 9 molar. And we've been working in molarity the whole time. I just didn't make a big deal out of it. I figured square brackets was a giveaway. Okay. Now we're going to try to solve problems. Now we know we have all these skills under our belt to solve acid-base problems. When you've got a reaction that's given to you, you say, what are the major species that are in solution before the reaction occurs? Okay, major species. Then you think about, all right, what are the possible reactions that could occur? Right? And they can be ridiculous if you want them to be, because you're going to throw them out anyway. And then you say, what is the dominant reaction? That's the key. Then you ask yourself one of two questions. Is it an equilibrium reaction, or is it one that essentially goes to completion? If it goes to completion, then you approach it one way. If it's an equilibrium reaction, then what we may do is go to completion and then work our way back. That seems to be an easier fix to a problem than trying to work equilibrium from the get-go. Then you react all your major species until you're left with an equilibrium equation. Then you solve for pH if that's the question. All right. So let's kind of ease our way into this. Consider a solution of 2 times 10 to the minus third molar HCl. All right. Easy. Major species. You have H plus, Cl minus, and H2O. Okay, I said before the reaction. Before the reaction, it's HCl. After the reaction, you end up with hydrogen ions, chloride ions, and water, because there's no HCl left. It's a strong acid. So the pH then, we just take the value of 2 times 10 to the minus 3 molar, because the dissociation is 1 hydrogen ion for each HCl. So we can equate 2 times 10 to the minus 3 as the hydrogen ion concentration and calculate a pH of 2.7. All right. What if we have a 1.5 times 10 to the minus 11 molar solution of HCl? Major species, same major species, pH of 10.8, which means this is a basic solution. If you made your solution with HCl, you would expect it to be acidic, right? But for some reason, we found that the HCl concentration is 10 to the minus 11th. That should have been a giveaway. If it's not larger than 10 to the minus 7, it's going to be basic. Right? So we calculated a basic pH. All right, when we add nitric acid to water, which is a strong acid, we get hydroniums, or hydrogen ions, and nitrate ions. So what we're trying to do here is to get you to think about what are reasonable reactions and what are unreasonable. If HNO3 is a strong acid, then NO3 minus, the conjugate base, is a very, very weak base. So it will not react with water in this way. Right, we can throw that one out. Now, what reaction controls the pH? Well, we always have this reaction. I mentioned that earlier, where water is amphoteric, right? It self-ionizes. That's always there. But is water the major contributor of hydrogen ions? That's the question. All right, if we have this pH, calculate the pH of this concentration of a solution. HNO3 at 10 to the minus 2, it's going to be acidic. Does the self-ionization of water have any significant impact on this reaction? The answer is no. Right, because it only self-ionizes to the tune of 10 to the minus 7th molar. And this is 10 to the minus 2nd molar. That's 5 orders of magnitude stronger. So we can ignore water in this case. And just calculate the pH based upon that concentration of HNO3. All right. I just put these steps in here so that you can go back and review them if you want. It's going to make more sense for us to work the problems. All right. We may even have to use an ice table. How about that? Okay, let's suppose we have a 0.8 molar aqueous solution of hydrocyanic acid, and there's the Ka. What are the major species? Well, when we put it in solution, the major species are going to be HCN and water. Those are the major species. Right? H plus and CN minus are not major species because the K value is so small. Right? So, if we compare the hydrocyanic acid reacting with water and water reacting with itself, we find that the hydrocyanic reaction with water is 3.5 orders of magnitude stronger than water. So we're going to focus on the HCN reaction. Right? That one controls the pH. So now if we have a 0.5 molar aqueous solution, oh, that's as far as that one goes. Right, give you whiplash. We're switching to HF now. So if we calculate the pH of a 0.5 molar aqueous solution of HF with a 10 to the minus 4 Ka, right, we say major species has to be that because it's 10 to the minus 4. It's a weak acid. And we compare the reactions, right? We're still 10 orders of magnitude stronger. Well, actually, maybe closer to 9. 9 orders of magnitude stronger for the HF, so that controls the pH. Now we go to our ice table. So what are the initial concentrations? Well, we say HF is the major species, right? And that's where we're starting. And since it controls the pH, we're going to essentially say that hydrogen ion concentration is 0. We know there's a little bit in there, but it's not significant. So then the change is going to be, we're going to lose a little bit of HF as it ionizes and gain some hydrogen ions and some fluoride ions. And there's your equilibrium expression that we can set equal to our K value. Okay, so there they are. Plug in the numbers. We're going to say, we're going to see that squiggly equals. That means that the K is so small that we're going to ignore X as a factor in 0.5 minus X. It's much, much smaller. X is going to be so small, it's insignificant compared to 0.5. So that's where we make the assumption. And we do that so that we don't have to deal with quadratics. So once we calculate X, we find that it's 1.897 times 10 to the minus 2. And if that's correct, then we were correct in making that assumption. The only way to be absolutely sure, to prove it, is to subject it to the 5% rule. I'm not sure if I did it in this slide or not. but calculating a pH is 1.72. Now, did I do the 5? Yeah, there we go. Okay, so how do we do the 5% rule? You take your value and stick it in for X of the true expression. X times X over 0.5 minus X. Put that value in there. That will calculate a Ka using your values. And then you compare that Ka to the accepted Ka, 7.481 versus 7.2. And then you ratio the difference. Subtract one from the other and divide it by the true value and see, is it within 3.9%? Well, is it within 5%? And it is 3.9%. So we're pushing it a little high, but according to the rule, it's okay. Now, how would we get closer? You get closer by substituting, you would say this value, X, leave those alone, and instead say 0.5 minus the value that you got, 1.897 times 10 to the minus 2 equals the K value, 7.2 times 10 to the minus 4. Then solve for X. That's called successive approximations. We made this approximation by claiming that X was 0. Now that we have a value for it, we're going to put it in there and then recalculate X. And that should be, let's just do that. I'm curious now. I want to see how close it is. So let's see, 0.5 and then 1.897 exponent 2 minus, that's 4.81 times 10 to the minus 1 times 7.2, 10 to the minus 4, and then take square root of it. So I get 1.86, 1.861 times 10 to the minus 2 equals. And if you put that one back into your 5% rule, it's going to be less than 1. It'd be a fraction. But that's how you get closer to the true value, this approximations. Okay. Throw another concept at you. Let's see. Let's go back to chapter 13 when we talked about equilibrium constant versus equilibrium position. Right? They're two different things. They're related in some ways, but equilibrium position can be entirely different for this set of starting conditions versus this set, but the outcome when you put it into the equilibrium expression is exactly the same. It's just you have different concentrations in equilibrium with one another. That's equilibrium position. Okay, percent dissociation, or actually ionization for an acid, is a ratio of the molar concentration of the amounts that's dissociated or ionized divided by the initial concentration. And this value is different. It changes depending on the acid concentration. Right? What we find for weak acids is that this value, percent dissociation, increases as your concentration of the acid decreases. Okay, that seems counterintuitive, but I hope we can show you how it works in just a minute. So, if we have a solution of 8 molar formic acid, right? You know, the stuff that's in fire ant bites. In fact, formic is from the Latin for ant. That's where it got its name. CHEM102, which is the simplest carboxylic acid, like CH, like that. That's your formic acid. 8 molar We got 8 molar concentration. And we're told that it's 0.47% ionized. 0.47% ionized, which means what? Which means total, or initial, I should say. Initial concentration. And then that's the denominator for the ionized amount. So 0.47% of this becomes that. And then this is still 8. Okay? All right. So that's why when we set up our ice table, we say that the amount that changed is 0.0047, which is the decimal equivalent of 0.47%. Okay, times 8. That's how much was lost from the original. Right, so we're subtracting that much. And since it's a one-to-one relationship, it shows up as hydrogen ions and formate ions. And then we just do the calculation. We find that at equilibrium, we have 7.9624 formic acid undissociated or unionized. And then we have 3.76 times 10 to the minus 2 for the other two terms. Right? If we plug those into our equilibrium expression, we can calculate what Ka is. 1.7 times 10 to the minus 4. All right, now that we have that, right, this concentration gives you that ionization. Then we can use the Ka. We're going to calculate pH first. All right, calculate pH, 1.42. So it's really acidic. Right? Maybe that's why fire ant bites hurt so much. They start your nerves jittering. Okay, the value of Ka for 4 molar, right? Half of this, what happens to the Ka? Nothing. Ka is a constant. It's a different equilibrium position, yes, because we start out with 4 molar instead of 8 molar. But the Ka is the same. That's a constant. How about the percent ionization? Well, based upon what you've been told, we haven't proved it yet, but based on what you've been told, if we decrease the concentration here, this ought to go up. All right, should be higher. Is this my proof? We've got a generic acid being dissociated. Okay. We got its Ka calculated here. I thought we were going to use we're going to do it symbolically first, and then we'll prove it, but with numbers. So there's your Ka. Right. The concentration of HA is roughly the same as when you started, right? Because the Ka is so small. And we're saying that H plus and A minus are essentially equal to the unknown value. Right? So if we put that into an expression for the initial condition, there it is, and that's typical, right? For weak acids, we usually do that. Just get rid of the X in the denominator. All right, so that's the initial concentration. Now what happens if we add enough water to take the initial concentration to 1/10 of its original value? All right, so what happens to the concentrations then? All right, well, A minus and H plus, the new values are going to be 1/10 of the X value. All right, and the initial value of HA is also going to be 1/10. So which way will the reaction proceed? Right? If we say the reaction, what we've done is we've taken HA and we've gone to H plus and A minus. And we've diluted both sides. Right, we've taken 1/10 of both sides. So which way is it going to try to shift? It's going to try to shift equilibrium to this side. Oh, we're going to calculate Q. Okay. Let's make it mathematical so we can approve it. All right, so if we calculate the Q from these values, we get X, right? X divided by 10, X divided by 10, and HA 0 divided by 10. And then we resolve that issue. Now we get the Q is actually 1/10 of the original KA. All right? Okay. If Q is less than K, which way is it moving? That way. So in terms of just the ionization, percent ionization, this is going to be higher relative to this one. We've lost some of this one to make this one bigger. So when we put that into this equation, that number is going to be larger. Okay, hopefully that's the explanation for why percent dissociation, or more correctly, percent ionization, is an increase with a decrease in concentration. Now, what does that do to the actual hydrogen ion concentration? It doesn't make the hydrogen ion concentration higher than it was before. It makes the ratio higher. But the actual concentration of hydrogen ions will be lower because we diluted the whole thing by a factor of 10. Okay? So when we calculate the pH should be higher for this solution than it is for that solution. Yep. Okay. pH of 4 molar. If we the pH is going to be higher. Yeah. I forgot I had a slide for that one. Okay, and there's your explanation in blue letters. Okay. So if we actually calculate the percent ionization for a 4 molar formic acid, we go to our ice table, we set it up with our original 4. We make the change, and then we set up the expression with our now calculated Ka value. And we're going to get rid of the X in the denominator and calculate the value of X, which should be X. And X is going to be divided by 4, I think. Come on. Yeah, X is 2.665 times 10 to the minus 2 divided by 4. So now at 4 molar, we've got 0.67%. But the concentration is 2.66 times 10 to the minus 2 for X, which is hydrogen ion concentration. What was it before? Uh, 3.76 times 10 to the minus 2. So it is a higher concentration of hydrogen ions versus 2.2. I think it was 2.2, wasn't it? 2.6. So the calculations tell us that our intuition was correct, is that the percent ionization increased, but the actual value of the hydrogen ion concentration went down. But it's not a linear decrease, if that helps any. Okay, and we calculate the pH as 1.57. So it's become a little more basic by diluting it. Okay. Shift gears again. Now we're going to talk about bases a little bit. Arrhenius bases must have the hydroxyl in the molecule. Bronsted-Lowry simply say that the base is a proton acceptor. And we know that a base has a pH greater than 7. Basic solutions have pH greater than 7. These compounds, lithium, sodium, potassium hydroxides are strong bases. In other words, they essentially dissociate completely in solution. Calcium hydroxide is considered a strong base also, with one catch. Calcium hydroxide is not completely soluble. So what we're saying is that the part of it that dissolves is completely dissociated, right? There's a caveat there. So knowing that if you're told that the aqueous concentration of calcium hydroxide is this value, then you can work with that as a strong base. But if you're told we put 3 grams of calcium hydroxide in 100 milliliters of water, what's the pH? Well, you got to know what its solubility is. Right? You can do that with lithium, sodium, and potassium because just about any amount you put in there is going into solution. But calcium hydroxide is different. All right. Let's see. That's what we know up to this point. So if we want to calculate the pH of 10 to the minus third molar sodium hydroxide, we just calculate the pOH and subtract it from 14. And the pH is 11. Okay? Let's see. What do we normally take a break? Oh, it's time. Does anybody need a break? Or you want to finish this chapter at least, and then we can maybe break. Okay. So calculate the pH of calcium hydroxide. Well, assuming we've given the concentration, this is 1 times 10 to the minus 3 molar calcium hydroxide. All right, what's the hydroxide concentration? This is completely soluble. I mean, this part is soluble. So we know it's 2 times 10 to the minus 3 molar hydroxide concentration. Right? Now we can work with that. We can say, all right, what's the pOH of 2 times 10 to the minus 3? Subtract that from 14. And we get 11.3. All right. This is an equilibrium expression for the conjugate base of hydrocyanic acid, Cn minus plus water. How do we get it into this situation? We put it in as the salt. Right? We haven't talked about that yet, have we? What is the salt in chemical terms? I guess I can tell you, since I keep using the word, if we have an acid plus a base, right? We get a double exchange. We get H plus OH, which is water. And then we get B plus A. Sometimes it's soluble, and sometimes it's not. This is the salt. The cation of the base plus the anion from the acid makes the salt in chemical terms, and water. That's an acid-base reaction every time. So when I say salt, I don't mean table salt. I mean chemical salt. So if we take this one and put it in, actually that's a misnomer. If we put a strong conjugate base from a weak acid, get that in solution, we just need to do that to it. So we got something that won't react. Right? This is a spectator. This is in solution at a given concentration. It reacts with water because it's a very strong base. It takes a proton from water and leaves us with hydroxyls. And there's your Kb expression, like we did before. Let's see. Calculate the pH of 2 molar solution of ammonia. Well, if the Kb for ammonia is 1.8 times 10 to the minus 5, and there's our ammonia base. In this case, we just put straight ammonia in there. Like when they make this at the factory or the chemical plant, they just take pure ammonia and bubble it through water until they get a certain pH or measured concentration, and then they bottle it and sell it as ammonia cleaner. So when it reacts with water, we get the ammonium ion plus hydroxyls, and we can write the expression, right? Ammonium plus times hydroxyls divided by ammonia. And since Kb is 10 to the minus 5, that means that the X is going to be very, very small. And we sort of bypassed the ice table. But you can see the structure there is similar to the acid, right? X times X over 2 minus X. So the 2 is the molar concentration of ammonia minus the amount that was converted into ammonium and hydroxyl. So we're saying that X is very small, and then we can solve for X without having to go through a quadratic. And that's 6 times 10 to the minus 3 is the molar concentration of hydroxyl. Calculate the pOH, subtract it from 14. In this solution, 2 molar ammonia is going to be a pH of 11.78. Within 5%, I'm sure. Okay. We don't have to spend a lot of time on bases. They're fairly well behaved. Terminology. When you have an acid that's like this, or like this, or even like this, right? These are monoprotic. Okay? If you have one like this, right? This is diprotic. Or if you have one like this, right? Then these together, we can call them polyprotic. Now, mineral acids, that's what we call these, mineral acids. Well, that's not a mineral. Mineral acids, I don't know of any that go higher than 3 protons. Right? Organic acids can go, the sky's the limit, because the really big organic molecules can have an acid hydrogen over here and here and here and here, all over the place. The other point that this slide is trying to make is that when, say, let's take phosphoric acid. When phosphoric acid goes into solution, and I'm going to simplify this, I'm not going to react it with water. I'm just going to say phosphoric acid in aqueous solution is in equilibrium with HPO4 minus plus H plus. Okay, and there's a K associated with that. Ka1. Then it's still in solution, right? We can take this one. Oops, sorry. Then we can take this one, and it will also lose a proton. And it will have a K associated with it as well, a different K value. Then we can take this one, because it's still in that solution with all those water molecules. It can lose proton to another water molecule and give us PO4 3 minus plus proton. And this also has a K of its own. Let's do better than that. Okay. For any acid that undergoes multiple ionizations, the size of the K values. This one is always larger than the second one, which is always larger than the third. Now, theoretically, you could have some that are very close to each other. And you may run across a chemistry problem here and there that says, okay, say they're equal. What does that mean? But in reality, the second one's smaller than the first one, and the third one's smaller than the second one. And typically, this one is the pH determining one, because these will more than likely be 3, 4, 5 orders of magnitude weaker than this one. Now think about it logically, right? This proton, this molecule doesn't want to give up its proton, so it's a weak acid, so it has a value there. But once you get to this, once it's negatively charged, how much more difficult would it be to remove a positive from that? Much more difficult, right? So this one is always smaller. And then now you've got a 2- charge. You're trying to make a proton leave that one, right? So it becomes more and more difficult as the charge increases. All right, and here's the relationship for phosphoric acid. 10 to the minus 3, 10 to the minus 8, 5 orders of magnitude. 10 to the minus 13, another 5 orders of magnitude. So 10 to the minus 13 is 10 orders of magnitude weaker than 10 to the minus 3. All right, there's your Ka1. So if we have a 1 molar solution, the pH is going to be determined by this one. And we can use this expression to find that the hydrogen ion concentration is that. And I think we missed the 5% rule on this one. Yeah, we're over 9%. Okay, so what do? Successive approximations. So we substitute x in that denominator, and we leave the x in the numerator alone. And recalculate. Now we're under 1%. Okay, so successive approximation works here quite well. So now that we know the x value, or the hydrogen ion concentration, is 8.27 times 8.28 actually, times 10 to the minus 2, we can calculate the pH from that. And the pH of this solution will be 1.08. Now let's see, are we going to, okay. Now that takes care of the pH, where we're calculating this concentration. But if we want to know what this is, we've got to step through to get to that point, right? Using each of the Ks. So PO4 3 minus in a 1 molar solution would be what? Okay, there's our first, actually our second. We know what it is for this one because we just calculated it. So now we're going to take those values and put them in here and calculate the next x, which is this one. And then we'll put it in here and calculate that one. Okay. So now for the second reaction, the second proton ionization, we get an HPO4 2 minus value. Oh, hold on a second. Okay, so see what has happened when we set it up and we approximated. The 8.28 times 10 to the minus 2 cancels out. So x is actually equal to the Ka. So now we can put that Ka in here and calculate, excuse me, I skipped a step. Then we can calculate we have to calculate a new H plus, which is essentially the same. Then we can go to the ice table that's not up there, set up the same arrangement, and we determine now that the PO4 3 minus is 10 to the minus 19th molar. Very, very small. This is for classes that have meet more than once a week. So now, I mentioned this already, so we don't have to go into much detail here. The chemical definition of a salt is one of the products of an acid-base reaction. When you react an acid with a base, you get a double displacement or double replacement, where the cation from the base is combined with the anion from the acid, and that gives you a salt. And the example here we're using sodium hydroxide and hydrochloric acid gives us table salt. So what do we do with these salts? If we have a salt and we put it in solution, what kind of pH can we expect, right? Or what can we expect, an acid solution or a basic solution? If the salts are derived from strong acid, strong base reaction, you will get a neutral solution. That's a rule of thumb. If, on the other hand, your salt is derived from strong base, weak acid, right? If we had H here and we had OH here, right? This would be the weak acid, strong base. Then the rule of thumb says this solution will be basic. All right. If, on the other hand, we have a something like this, right? This is derived from a strong acid, and this is derived from a weak base. Then this solution will be acidic. Okay, those are rules of thumb. I'm going to explain why it works. Chemically speaking, derived from a strong acid, weak base, or a weak base, strong acid, does not explain the chemistry. It just makes it easier to determine the outcome. All right, here's how it works. Let's use acetic acid, for example. All right. If we put acetate, sodium acetate in solution, right, plus water, and this is going to be a strong conjugate base, correct? And this is derived from the sodium salt, right? So we get this in solution, react with water, and it produces the weak acid plus hydroxyl, right? Derived from a strong base, weak acid. We said, rule of thumb says the solution is going to be basic, but it's not based upon, the outcome is not based upon this basic here. It's based upon this strong base here. This strong base removes a proton from the water and gives us a hydroxyl. That gives us the basic solution. So that's the chemistry, but the rule of thumb works. We run into a problem when we've got a solution that's derived from a weak base and a weak acid. All right. In that case, you have to know what the Ka and the Kb are for the acid to base combination and compare them. Now, here's a helpful rule. If the Ka for the weak acid is equal to, numerically equal to the KB for the weak base, then you're going to get a neutral solution because there's no winner. Let's see if I got it on the next slide. I think I do. This is qualitative prediction based upon our rule of thumb. So we're going to skip that. We've already done it. Let me see. Let me skip this for a second. Oh, we got that to go through. I was looking for, I bet what I'm looking for is in the problem sets. So I'll save that. Oops, I want to go back. Here we go. Here. Calculate the KB values for C2H3O2 acetate ion and the cyanide ions. I'm not sure why they want us to do both of them. Depends on the reaction, I think. Okay, so the KB for the acetate ion is 5.6 times 10 minus 10. Okay. And for the cyanide ion is 10 to the minus 5. So the cyanide ion is a stronger base than the acetate ion. Right, see, the value is bigger. Now, if we go, I think we're switching gears on you here. If we want to arrange these 1 molar solutions of these acids from lowest to highest pH, we can do it qualitatively. We can examine the electronegativities and the acid-base strengths of the ions. And the first question we ask, if we're doing it qualitatively, are there any compounds composed of ions from strong acid, strong base interactions? Strong acid, strong base. That would be neutral, right? Sodium chloride, sodium hydroxide, hydrochloric acid. Yes, so that would be neutral. That would be right in the middle at pH 7. Okay. Lowest to highest pH. So this would be more acid, this would be more basic. So the pHs are going to be bigger on that side and smaller on this side. Next, okay, are there any strong or moderately strong bases out of this group? Well, sodium hydroxide is definitely strong. Sodium hydroxide ought to be way over here. That's definitely very basic. Moderately strong bases. Maybe ammonia. Yeah, ammonia. Because ammonia is a pure base, right? It's not a salt. So the pure bases are going to lean toward this side. We already calculated a 1 molar solution of this. It was over 11, wasn't it? It was way up there. Okay. So we got those taken care of. Now how about, are there any compounds of ions from weak acid, strong base interaction? Weak acid, strong base interaction. Sodium cyanide. Yeah, weak acid, strong base interaction. Sodium cyanide should then be in this region. Okay. Let's see. Next, are there any acids derived from halogens? Yeah. Hydrochloric acid. Those are going to be strong acids. HCl. Oh, wait a minute. There's no HCl in there. HBr. There you go. HBr is going to be way over here. Very low pH. HF is, yes, HF is derived from a halogen, but HF is weak. I don't know if I've explained this yet, maybe in other terms. HF, we would expect the acids formed from halogens to get stronger as you go up. Let me see, does that make sense? We've got the same charge, -1, -1, -1, -1. We're getting bigger ions as we go down here, so the negative is more diffuse. Actually, this should be strong. Strong, less strong, less strong. Okay, so that trend is correct. HF is going to be a weak acid. Even though it's a halogen, it's going to be weaker than HBr. So HF then would be, where is it? Come on. There it is. HF is going to be in here. Okay. Now, what do we have left? We have HCN and ammonium chloride. So now we got to decide between those two. HCN is a weak acid. It has a higher pH than either one of these, which is where it should be. While ammonium chloride is the salt of a weak base and a strong acid. So it's going to be acidic. It could be that HCN is more acidic than ammonium chloride simply because it's an acid. Ammonium chloride is a salt. So that's kind of a guess. HCN. The only thing that would confirm that is numbers, K values. All right, so that's where our intuitive assessments have gone. Now, if we look at it in terms of the K values, we find that the HBr is a strong acid, HF is a little weaker, 10 to the minus 4, HCN is 10 to the minus 10, but ammonium chloride, K value, we really shouldn't say Ka for that because it's a salt. But the K for that value dissociates a little bit less than HCN. Then we got neutral, and then we go to the KBs, because now we're talking about the KB of this, KB of that, and the KB of this. So by comparison, the K value for this one is smaller than this one. 1 to the 0.6 times 1 versus 1.8. So the numbers confirm our assumptions. Two ways to solve that problem. All right. Consider a 0.3 molar solution of sodium fluoride. The Ka for HF is 7.2 times 10 to the minus 4. What are the major species? Well, we have sodium, fluoride, and water. HF, now why don't we have HF in there? Because this is a very small value. We ought to have HF in there. Why isn't sodium fluoride considered a major species? Oh, I'm sorry. Y'all should correct me. We're talking about sodium fluoride. Sodium fluoride is not a major species because it completely dissociates in water, right? All sodium salts are soluble. All right, that's why it's not a major species. So what are the possibilities for reactions, right? We take the fluoride ion, react it with water. We can take water and react it with itself. We can take sodium reacted with water. That's kind of ridiculous. sodium reacted with fluorine ion. Sodium reacting with water is ridiculous, right? Sodium hydroxide is a strong base. It's going to be completely dissociated. It doesn't care about water. Sodium reacting with fluorine, it doesn't care about that either, right? Because it's a soluble salt. It produces those independent ions. That's it. So we got these two reactions to compete. Now we want to compare them, right? Which one controls the pH? The fluoride plus water, or water with itself. We need to know what's the Kb for that fluoride with water. Well, we know what the Ka is, so we have to calculate the Kb. Kb is 10 to the minus 11, and water is 10 to the minus 14. So the fluoride reaction is 1,000 times larger than the K for the water. So we know which one controls the pH. It's the fluoride reacting with water. All right, there's another one. We were going fine, and then it switches gears. So now we're looking at sodium cyanide. We're going to go through a similar procedure to find out what are the major species. Right, there they are. Then we propose these equations, and we throw out these ridiculous ones. Now we've got a competition between the cyanide ion and water. Right, Kb for cyanide, we calculate that Kb 10 to the minus 5, which is much, much larger than the K for water. So we know the controlling reaction is cyanide plus water yields hydrocyanic acid plus OH minus. And we set up our ice table, and our calculation looks similar. And since that value for Kb is so small, we can throw away the X and calculate the X with the others as 3.46 times 10 minus 3, or 2.46 POH. And pH then is 11.54. All right, so that's how you solve one of these salt problems. Okay. So let's take a look at the way we describe acids and bases, two factors that affect whether the strength of the acid or the base. One is bond polarity. How strong is the bond? The weaker bond is going to give up protons easier. Right? Remember, bases, well, the ones with hydroxyl in them, are ions already. Right? So all they have to do is split apart. We're talking about bond polarity, strength of the bond, and bond polarity in my mind's gone blank. What's the companion to ionic bonds? It's covalent, excuse me. Covalent bonds are what we're discussing here, the bond polarity versus the bond strength. And we're fixed on acids right now. So the bond strength of for halogens, and remember, halogens, they can only have one hydrogen for their acids. That's it. So the bond strength there decreases as you go down from fluorine, chlorine, bromine, iodine. That means that we're going to get a stronger and stronger acid as the bond strength decreases. And that's probably because the negative charge is more diffuse over a larger ion. Okay, that was bond strength. And that would naturally decrease the polarity of the bond too. HF bond is extremely polar, but the bond strength is very high also. Okay, oxyacids. What's an oxyacid? Well, it's one where the acidic hydrogen is bound to an oxygen, right? So let's see, how about ClO3 minus, which would be the chlorate polyatomic, right? we add a hydrogen there, that would be chloric acid. Right? Chloric acid. That is an oxyacid. That hydrogen is actually bound to that chlorine. Let's see, chlorine, and we have 1, 2, 3 oxygens and hydrogen. Like that. Oh, I'm missing one. Needs to go right here. There we go. Okay, now we're right. So this is an oxyacid. The strength of the acid increases with an increasing number of oxygen atoms. So if we go up here with the perchlorate, and that makes perchloric acid, we get ClO4 minus, and then we add the hydrogen. All right. If we take away one, right, I'm going to skip this part. This makes chlorous acid. And if we take away another one, O, this makes hypochlorous acid. And the acid strength decreases this way. Now, there's a perfectly logical explanation for that. It has to do with the electronegativity of oxygen. You have one oxygen here. Chlorine has a fixed electronegativity. So if oxygen is bound, oxygen, actually this hydrogen is bound to that oxygen, then the chlorine and oxygen are pulling electron density away from the hydrogen and weakening the bond. If you add another oxygen out here besides the one that's bound to the hydrogen, then you're pulling even stronger. Stronger pull, the strongest pull of this group. Pulling electron density away from that bond and weakening the oxygen-hydrogen bond. That makes it more acidic. So we find that perchloric acid has a very, very large K value, greater than 10 to the 7th. Chloric acid is 6 orders of magnitude. And then these become weak. And we can use the same reasoning for sulfuric acid versus sulfurous acid, nitric acid versus nitrous acid. Anytime you add an oxygen, you increase the acidity of the homologous series. Now, if we, rather than doing it this way, where we add oxygens, let's say we keep it simple, right? We stick with this one, right? One oxygen, and then instead we change the halogen, right? So if we go from chlorine to bromine to iodine, then the electronegativity, right? Remember the periodic trend, periodic trend for electronegativities is it gets greater from lower left to upper right. So in a column, the electronegativity is decreasing as you go down. So decreasing that electronegativity hold on a second. That doesn't make any sense. Yeah, it does. Okay. We're decreasing the electronegativity. The Ka of the acid also decreases, becomes weaker. weaker acid as we decrease the electronegativity. I don't know why they put a methane in there. Maybe that'll become an issue when we study organic. There's no fluorine in there because it's unstable. It decomposes to HF and hydrogen peroxide in water. So you really can't get a measurement of that one. Okay. Now, when we talked about oxides of compounds that go into solution, what happens to them when they go into solution? These acid oxides are oxides of nonmetals. In this case, we've got sulfur, nitrogen, and carbon. Those oxides produce acidic solutions when they react with water. And at the bottom, we have an example. Sulfur dioxide reacts with water to produce sulfurous acid. And that's typical. If we used carbon dioxide reacting with water, it would produce carbonic acid. Right? That's what it does in pop. When they force carbon dioxide into your drinks, it makes carbonic acid, which is a weak acid. I mean, there's no danger to you. They put a little phosphoric acid in there too, probably to stabilize it. Actually, that's what, if you take Coca-Cola and put a nail in it, come back in a week, it's gone. It's not from this acid, it's from the phosphoric acid. Okay, those are the acid oxides made from the oxides of nonmetals. Oxides of metals, on the other hand, when they react, they produce basic solutions. So here's the example of a potassium oxide. When it reacts with water, it produces potassium hydroxide. And that's where the basic comes from. All right. We talked about Arrhenius bases, Lowry-Bronsted acids and bases. Now we're going to talk about Lewis acids and bases. So I think Bronsted-Lowry acids and bases. This is an acid is a proton donor. A base is a proton acceptor. This is how I keep it straight. When this acid donates a proton, it becomes what? Proton separates and leaves behind an electron pair, right? Because there was a bond here, right? When you break that bond, this electron pair goes over here. Well, one of those electrons was already part of the neutral A, but the extra electron from that pair makes the negative. Okay, so the electron pair donor, electron pair acceptor actually, accepts the electron pair into this. So the Lewis acid is an electron pair acceptor. For a base, right, we're going to make this positive and this negative, right? So the negative stays with the hydroxyl and the sodium becomes deficient. This is a base is an electron pair donor. So it's just the flip side. Bronsted-Lowry, proton donor, electron pair acceptor. Base, proton acceptor, electron pair donor. The usefulness of the Lewis definition is that you can have electron pair movement in a reaction and there are no protons that do any moving at all. Like this example where aluminum is the acid, the electron pair acceptor. It accepts an electron pair from water. Water then is the Lewis base, the electron pair donor. Okay, and it's very useful for organic chemistry where you don't have significant amounts of proton movement, where you can speak of it in terms of acid-base reaction based upon the electron pairs rather than the protons. Actually, you can have some reactions, protons are nowhere to be seen, right? And you can speak of it in terms of acid-base, which is convenient. All right, that summarizes things. Oh, I left that point out. It allows you also to conduct reactions in non-aqueous systems and speak of them in terms of acid-base reactions. Right. Up to this point, we've been focused on aqueous solutions, right, where water is the solvent, but it doesn't have to be. Right. And many organic reactions are conducted in non-aqueous systems because we don't want water as a reactant. Water as a reactant is a competitor that ruins the outcome of the reaction. So we conduct the reaction in non-aqueous solutions, but we can still speak of them in terms of acid-base reaction as long as we use the Lewis definition. Okay. That was just a reminder of what we did. The funny part for me is chapter 15 is acid-base equilibrium. And we've been talking about equilibrium the whole time, almost the whole chapter 14.
Feels like it.
Yeah. I think probably what they should have done is rename this acid-base buffers, because that's where we're headed with chapter 15. All right. 2 ways to shift an equilibrium in terms of concentration effects. Right. You can change the reactant or product concentrations directly. Right. That's an option. Or you can change the equilibrium by coupling with another reaction. And that's what we're going to do when we come back after break. The Le Chatelier's principal lab, which is an informal lab. There's no formal report for this one. Yes, that one. Several of those reactions in there, we changed the concentration of the reactants in our main reaction by coupling it with a second reaction that changes the concentrations in the first reaction. We couple a reaction. In order to do that, we have to have a common ion that's involved in both reactions. And the common ion effect is essentially shifting the equilibrium position by the either addition of an ion or removal of an ion directly or with the coupled reaction. This is Le Chatelier's principle. Okay, so in this case, if we have this solution of hydrocyanic acid and we add sodium cyanide, which way will the reaction shift? Well, sodium's not involved in this reaction at all, but the cyanide is. So if we increase the concentration of cyanide through the addition of sodium cyanide, we will shift the reaction to the left as written. And that's an important point that I want to make, is shift to the left or the right as written. If we flip that reaction, then left means right and right means left. So if you're going to reference the movement of equilibrium in a reaction, a balanced equation, then you need to have that balanced equation right there with your conclusion. So that when you say left or right, then we know which equation you're basing that movement on. And I just ended a sentence with a preposition. English teacher rolling over in the grave. Okay. So what effect would that have on the pH of the solution or the acidity of the solution? Well, if we add sodium cyanide to the solution, it's going to shift the reaction to the left, correct? And it's going to consume hydronium ions, which are responsible for acidity. We're going to remove the hydronium ions or the hydrogen ions from solution, and that will increase the pH, decrease the hydrogen ion concentration. It will decrease the acidity. Okay. What do we mean by a buffered solution? Well, buffering is discipline dependent. In other words, a buffer to an engineer in a chemical plant working a certain type of reaction will mean one thing, and to another one in another plant will mean something else. We're going to focus on a specific type of buffering called pH buffering. And when we do that, then our definition narrows to include only reactions which resist a change in pH when an acid or a base is added to the solution in equilibrium. Most often, buffered solutions are made up of the conjugate base, the weak acid, and its conjugate base in the proper combination. So if we said something like this, we have this reaction to go on, right? And it's in equilibrium, and I'm leaving out the water just for simplicity. Right? So we have a certain concentration of acid and its conjugate base in solution. The reason that you need both of them is the fact that one is responsible for buffering the solution when you add acid. The other one's responsible for when you add a base. So we need both of them in solution. Now, how do we do that? Well, two ways. You can create a solution of acetic acid, or vinegar, and you can add a base to it and remove hydrogen ions, right? Add hydroxyls, remove hydrogen ions, and as you do that, you produce some of this. And at a certain point, you would have sufficient number of those and those to make a buffering solution. Or you can combine a certain amount of this and say the sodium salt of the acetate ion. And then you don't have to titrate. You don't have to neutralize any of the acid. You just put them together in the right combination and you get your buffer right there, instant. All right, so what is a buffered solution going to do if I add acid? Okay, this buffered solution is now in equilibrium. So if I add acid, it's going to enter the common ion here is hydrogen ions. So it's going to enter here, and we're going to increase this amount. So what's the reaction going to do? It's going to shift this way to reestablish equilibrium. And what does that do? That consumes some of these, not all of them, but some of them. And since these are responsible for pH, then the pH is not going to change that much. It'll change a little bit, yeah. We don't say that the pH is fixed in a buffer solution. We say it resists a change. And it resists the change because this is a strong conjugate base. And this is a weak acid. So when we add these protons, that strong base is going to latch onto them until we reach equilibrium again. Okay? That's how it buffers addition of acid. What if it adds, if we add base? If we add base, then this produces water. And we know from the equilibrium expression for water dissociation that it prefers to be like that, doesn't it? Prefers to be water. So this hydroxyl and that hydrogen ion combine very effectively to produce water, and the shift then is to the right to replace some of that and give you some more of that. And since the pH is based upon the hydrogen ion concentration, then we're replacing some but not all of those hydrogen ions until we reach equilibrium again. So that reaction, shift to the right, holds the pH for addition of a base. When we add an acid, then the shift is to the left to reestablish equilibrium and hold pH for that addition of an acid. Okay. All right. Let's see. That's what I was saying here. Okay. Now, let's simplify things with an equation. First, after Sorensen proposed his, well, actually, before Sorensen proposed his pH, a chemist by the name of Henderson took this reaction and was interested in the hydrogen ion concentration. So he simply took the expression here of Ka equals H and then A minus over HA and solved it for hydrogen ion concentration. So if we do that, I'm going to put the hydrogen on this side. And that means cross the equals, we flip it. So we have Ka times HA over A minus. Or we could say Ka by itself plus this ratio, HA over A minus. Okay, so that's Henderson's equation. Hydrogen ion concentrations equals Ka plus the ratio of unionized acid to the conjugate base. And I think that's the first step here. Yeah. There we go. So that's Henderson's contribution. When Sorensen proposed pH, then Hasselbalch came along and he said, okay, I like the way that looks, but I don't want to deal with all the scientific notation. So he said, why don't we do this? Let's just say negative log of the whole thing. Okay. So that's where Hasselbalch came in. Is it LCH? Yeah, it is. LCH. Hasselbalch came along and did that transform. So negative log of hydrogen ion negative log hydrogen ion concentration is pH. Okay. And then negative log of Ka is pKa. And then negative log of this expression, I'll explain it in just a second. This ratio of these concentrations, we don't want to turn them into PHA and PA minus. That's just a little too far. So we leave this alone, except we don't like negatives. So we're going to change this to a positive. What does that do to the expression? Well, the negative log of A over B is the same as the positive log of B over A. That's another logarithm trick. So Haselbach said, here's my final equation. Plus the log of the conjugate base over the concentration of the weak acid at equilibrium. And this is Henderson-Haselbach equation. Took several years to get there, but eventually that's where we settled. Henderson, 1908, and then Sorensen came along with his pH, and then Haselbach modified Henderson's equation. Here we go, and there we go, and there we go. So that should be fairly easy to derive if somebody happened to ask you to do that on a test. Right? The advantage to this is that the calculation is simplified. We don't have to go to an ice table. As long as we know what these concentrations are, and we know what this is for the weak acid, then we can calculate the pH for that solution. Okay. So for all buffered solutions for a given weak acid, this conjugate acid-base pair ratio is the key. And for any given pH, since this is fixed, this is a constant, for any given pH, this ratio will always be the same. Now, it can be a large, or it can be a small, small. But the ratio is always the same for a given pH and for a given weak acid. So here's an example. What's the pH of this buffer solution that has 0.45 molar acetic acid and 0.85 molar sodium acetate? So we added the acetate through the sodium salt, and we added acetic acid as is. And the Ka is 1.8 times 10 to the minus 5, so we just take the negative log of that. And we insert those values in there, and we find that we have a pH of 5. Now, we could do it by ice, end up in the same place. Okay, this is, we already talked about this. What happens when you add an acid and what happens when you add a base to a buffered solution? We haven't talked about the ideal buffer contagion. The ideal ratio. Okay, that doesn't do it. Before we talk about buffer capacity, I mentioned earlier there were two ways to give you this and this in solution. One way is just to add this as the salt along with the weak acid, like we did in a previous problem. The other way is to titrate it. So if we take a solution, and this is the pH of the solution, and this is we're going to use a weak acid, so this is added base, right, or hydroxyl ion concentration. If we start off with a weak acid, the pH is going to be down here somewhere, right? And it's going to start off like that. And then as we start producing some of this in solution, then it begins to buffer itself and the pH stops changing. But initially it does go up. But as we add more base, we reach this relatively flat plateau in here. This is the buffer region. And then we get to the point where we've used up, adding the base, we're using up most of the acid. And now the pH starts to really jump. because we're adding base that's not being buffered. So the pH is going to go like that, and then it'll level off at the top. Right here in the middle is the equivalence point. That's when the added base is equal to the acid. Okay, so if we add enough OH to completely neutralize that acid, this is the point right here. So this amount of base right here is the equivalence. And sometimes we use that relationship to determine the concentration, an unknown concentration of acid. If we know the concentration of base, we can add it to the acid and calculate what the concentration of the acid was originally. But for buffering purposes, we want to end up in this region right here. Well, as it turns out, the middle of this region right here is 1/2 equivalence. That is, only half of the hydrogen, the weak acid has been neutralized. Right? So we got half of it's converted into this, the other half is that. So what does that say for this ratio? These two are equal, right? These two are equal. So if we divide that one, we get 1. Right? And remember, the common log of 1 is 0. 10 to what power is 0? 10 to what power is 1? 0. So that goes away. So at this point right here, this pH right here is the pKa. Okay. All right. So that says that the ideal ratio of A- to HA, or weak acid to strong conjugate base, is exactly equal amounts right in here. That allows you to move this way with a certain amount of base or to move this way with a certain amount of acid, and it keeps you in the buffer zone. All right. So that's your ideal, equal amounts. Now, it doesn't have to be equal amounts. Right? You can adjust it over here if you need a pH, because this is really not flat. It's kind of just gently sloping. So you can make adjustments to get the exact pH you want. Now, the concept of buffer capacity has to do with not the ratio, but the absolute amounts. So if the ratio is correct, but we want a large buffer capacity, then we increase this concentration, that concentration, equal amounts, until we get a larger amount of each. And that way you can put more acid or more base in there and still hold your buffer. Now, there are other issues that have to be dealt with, such as ion strength. Right? If you're using buffers in a living system, there are limits. Right? You can't increase the ionic strength of your solution too high for cells, or it'll kill them. Right? Or you can't increase it too high, or you exceed their osmotic pressure. And you either, if you exceed their osmotic pressure, then you shrivel them up, crenate the cells. But if you make it too low in concentration, then the water will move into the cell and the thing will explode. So living systems are a little trickier. Okay, buffer capacity can be calculated. It's the amount of proton or hydroxide ion, depending on whether you're building, you're introducing acid or base, that can be absorbed without a significant change in pH. And we can calculate that with this formula, buffer capacity. There it is. Beta stands for buffer capacity. So the ratio is the change in molarity, or the change in, actually N is normality, and we haven't talked about that yet. Change in normality is referencing the hydrogen ion concentration or the hydroxyl ion concentration. change in normality for each change in pH. Right, so if you can keep the pH change very low for a large value of change in normality, then you have a large buffer capacity. So the higher the beta value, the higher the buffer capacity. That's why it's set up that way. I don't think I'm going to ask you to calculate any of those. You just need to know it. All right. Maybe we don't talk about normality. Normality is a way of expressing hydrogen ion concentration or hydroxyl ion concentration independent of what acid or base you're putting in solution. If you have a 1 molar solution of HCl, 1 molar HCl in solution, what's the normality? It's 1 normal. Because you're putting the same number of protons in there as you are molecules. So 1 normal is relative to how many hydrogens there are in each the molecule. So if you do it for H2SO4, 1 molar is actually 2 normal hydrogen ions. I should put hydrogen ions. Okay. All right, choosing a buffer. So we're choosing a buffer based upon its pKa, right? Because this tells you where that flat spot is in your reaction. I was getting ahead of myself. Here's the equivalence point is also called the stoichiometric point. That is when you have equal amounts of acid and base. And that's in terms of hydrogen ion and hydroxyl ions. Right? If it's sodium hydroxide and hydrochloric acid, it's the same molar concentration of the molecules. But if you're reacting sodium hydroxide with sulfuric acid, then you've got a 2-to-1 ratio there, and normality helps you out with that because it's independent of the molecule. Half the equivalence point is where the buffer is best. All right. So here we have a titration curve of acetic acid with sodium hydroxide, and the half equivalence point tells us where pKa is. Let's see. I think we have a lab doing that, don't we? Or did we already do that one last semester? Oh, no, it's coming up after Le Chatelier. Yeah. We're going to take acetic acid and titrate it and determine what is the Ka of acetic acid based upon this curve. All right. Let's see. Yeah, we want the ratio of conjugate base to acid to be equal to 1. We want those concentrations to be equal. That means the pH now is equal to the pKa. We can do it with the titration of actually any acid. In this case, it's nitric acid. Actually, nitric acid, strong acid, and strong base. When you reach the equivalence point, we looked at this a little earlier. At the equivalence point of a strong acid and strong base, the pH is 7. The pH of acetic acid, this will be up in the high 8s. Now, if we titrate sodium hydroxide with hydrochloric acid, we're going to end up at the same equivalence point, except the graph is going to be inverted. It's going to be flipped because you're starting off at a high pH and you're adding acid to it. All right. Weak acid, strong base titration. The best way to approach this, we mentioned this very early, the best solution for this type of problem is to do the stoichiometry first. In other words, if you're told how much base is added to your weak acid concentration, then you say, all right, how much of the acid was neutralized by the base? complete all the way to completion and what's left over. That gives you a concentration of what's left of your acid and what's produced as your conjugate base. Once you have those values, then you treat it as an equilibrium. So here's an example. If we have 0.1 mole of hydrocyanic acid, and we mix it with 0.04 moles of sodium hydroxide in 1 liter, which means 0.1 molar acid and 0.04 molar sodium hydroxide, we want to, I'm not sure what we're going to find out. We're going to take it in steps. What are the major species? All right. So we've used up some of the, we're starting off with hydrocyanic acid, HCN. We're adding sodium and hydroxide to it, and there's always water in there. This is before the reaction. So during the reaction, we can get these possible effects, right? Water, of course, always. HCN and water produces cyanide. And then we can get HCN and hydroxyl because we've added base to it, correct? Yes, we've added base. All right, which ones? These go out, as usual. So now it's a competition between these three. Which one controls the pH? Well, after the reaction, we have some HCN left over, we have some cyanide, and we have some water and sodium ions. Well, shoot, it did it to me again. I was getting ready to solve the problem and it just switched. Now we're using acetic acid again. All right, so we're starting over again. 0.2 moles of acetic acid and 0.03 moles of sodium hydroxide in 1 liter. All right. So now those are our major species. Let's see. Well, this is before the reaction, so the acetate ions and the hydrogen ions are not. Well, the hydrogen ions are not going to be significant even after the reaction because they're being neutralized by the hydroxides. But we can throw away these bottom two again, and we compare the upper three. Which of these reactions really occur, then which one is dominant? Well, the one at the top, of course, Kw for that is 10 to the minus 14th. It's going to be insignificant based upon the others. The Ka for acetic acid, we have seen that one before, is 1.8 times 10 to the minus 5. And then we calculate the Kb. Let's see, Kb. Actually, that Kb is in the wrong direction, isn't it? It would be going back the other direction. The strong base hydroxide will react with the strongest proton donor, which is Hc2H3O2. All right, so if we go to completion, all right, here's what we're going to do. We're going to take this reaction to completion first. Okay. So this reaction here is acetic acid plus the hydroxyls, and we're going to use up all of the hydroxyls. The reason being that the reaction is shifting to the right, and we've got less hydroxyl than we do acid. Right? So all of the hydroxyls, we're going to use them up. That means at equilibrium, we're going to have 0.17 molar acetic acid and 0.03 molar C2H3O2. This is our equilibrium position. And we can either use an ice table for the follow-up equation. Is this one, right? We can use an ice table for this one, and we know what the Ka is for this one. And we can calculate the pH as 3.99. All right. So let's simplify it. Let's take those equilibrium numbers and plug them into Henderson-Hasselbalch. Right? We do that, we get the same value, 3.99 pH, and we didn't have to set up a second ice table to do it. But we did have to find out what the equilibrium concentration happens to be. All right. How about 100 milliliter solution of 0.1 molar acetic acid? Calculate the pH. All right. Well, okay. We use an ice table for that one. Let's see what the point is. Next page. Oh, okay. So this is just purely acetic acid. Calculate the pH as 2.87 using the ice table. Since we don't have any conjugate base in there, we can't use Henderson-Hasselbalch because that value would come up 0. So we have to use the ice table first to find out what's the pH of this particular solution, 0.1 molar acetic acid, and it's 2.87. Okay, now we're going to take that solution and add 50 milliliters of 0.1 molar sodium hydroxide to it. All right. Okay. We let the reaction go to completion. But in order to do that in an ice table, we have to calculate what the actual concentrations are. So the initial concentration of acetic acid is not 0.1 molar because we diluted it with another 50 milliliters of solution. So it's 0.1, it's 100 milliliters or a tenth times a tenth divided by 150 milliliters. See where that came from? Okay. We do the same thing for the hydroxide. Now we let that go to completion, right? As it turns out, we can use up all of the hydroxide and produce acetate ion, the conjugate base. And now our equilibrium position is 0.033 molar unused acid and 0.0333 molar acetate ion. Now that we know what the equilibrium position is, we can use Henderson-Hasselbalch and find that the pH is 4.74. And this, since those concentrations are very close to each other, acid and conjugate base, this is the best pH, buffer pH for acetate as your buffer. So if you need a buffered solution with acetate, then that's the pH that you want. Okay, how about 0.1 molar ammonia and 50 milliliters of 0.1 molar ammonium chloride? All right, so this works. Up to this point, we've used a weak acid and its conjugate base. Now we got a weak base and its conjugate acid to deal with. So we calculate the concentration. We're going to take this one to completion. The concentration of ammonia is 0.0667 because of that dilution factor again. And we're starting off with 0.033 molar ammonium. And we get our change. And the equilibrium then is has an unknown factor in it. So we got to figure out what that is. There we go. There we go. So we missed the 5% rule, or did we? No, it satisfies the 5%. I'm sorry. Satisfies the 5% with our estimation. We find out what the concentrations are. X is, wait a minute. We weren't making a buffer, were we? Yeah, we were. Yeah, because we added ammonium, which is the conjugate acid of the base. The weak base with its conjugate acid. Okay. So once we find out what X is, then we'll get the concentration of X is the hydroxyls, right? That's 3.6 times 10 to the minus 5. And then the POH is 4.4 and the pH is 9.56. So we didn't even use Henderson-Hasselbalch this time. If we had, we would have had to convert KB to KA. And then we have to decide which one is the base and which one's the conjugate acid to put them in I think that's on the next, yeah. If we use Henderson-Hasselbalch and we have these equilibrium concentrations, then we have to decide, all right, Ka now is 5.56, 10 to the minus 10, the pKa is 9.25. So then we can put 9.25 in there, but now which one is the acid and which one's the base? Well, the conjugate base is ammonia, and the conjugate acid is on the bottom, right? So instead of the right-hand number being on bottom, it's on top now. And we calculate the same value. All right. Another problem. What's the pH of a solution by mixing 1 liter of 0.5 molar ammonia with a Kb and 0.5 liters of 0.1 molar, and then add 0.1 mole of HCl gas? The reason we're saying add 0.1 mole of HCl gas is because it will dissolve in the water, but it won't change the volume. Okay. If we added HCl as a solution, then that would complicate the volume calculations. So, before we do anything, before we add any HCl, the ammonia concentration is 0.5 and the ammonium concentration is 0.1. Well, actually, no, the absolute amounts are 0.5 mole and 0.1 mole. Then we're going to set up a reaction, right? Now, when we add the HCl, which is 0.1 mole of hydrogen ions, reacting with the ammonia, then now what we have after that reaction is 0.2 mole of ammonium and 0.4 mole of ammonia. Now we calculate the concentration because equilibrium is based on concentration only. This just got us to the point where we can now calculate concentration. And that was an issue for, let's see, hadn't got there yet. That's going to be a method that we use for our complex ion, the last lab. Right. We'll talk about it some more when we get there. Okay, now if we calculate the concentration, the total volume is 1.5 liters. So now we have 0.267 mole base and 0.133 mole of acid. We can plug it into the Henderson-Hasselbalch as long as we calculate the Ka first. Then plug it in, and we get 9.55 pH after that reaction. Okay, let's see. We have acetic acid, and it's titrated with 0.1 molar sodium hydroxide. What is the pH of the solution at the equivalence point? That's always a good calculation to do. And the reason for that is when we're doing, if we have 100 or more titrations to do, and all we want to know is where's the equivalence point? How much base did we add? How much acid was there to begin with? That calculation requires that you know where this happens. And instead of using a pH meter and doing a separate titration for every one, we have machines that'll do that now. By hand, we would pick an indicator, something that would change color at that point. And if that's the case, then we go for it. Right? But we need to know what that pH is, and this is the way to find it. So since the equivalence is reached by titrating equal concentrations of acid and base, then the total volume, equal volumes, if they're the same concentration, are they? 0.1 molar acid, 0.1 molar sodium hydroxide. Okay, so we got equal concentrations of monoprotic acid and monohydroxyl base. So that being the case, we can say that we would reach equilibrium when the volume, we put an equal volume of each one. Right? 100 milliliters of acetic acid we need 100 milliliters of sodium hydroxide. The pollen was started already. Must be me. So we let the we do like this mental experiment trick, and we say we're going to put these together, but we're not going to let them react yet. So we're going to say the concentration before the reaction is 0.05 molar for each one. So that's what it is to start with. Initial is 0.05 molar. Then each one is used up, and we end up with 0.05 molar of the acetate ion. Okay, that's the stoichiometry part. Then we say, all right, if we have that, now the reaction is this conjugate base reacting with water. So we set up that reaction. And we have, after the reaction is done, we have 0.05 minus X, and then X and X. We find out what the KB is. So we know what the Ka is. We calculate the Kb because this is a base reaction, right? Conjugate base with water. So we need to know the Kb for this reaction, not the Ka. And then we plug in our values and find that the POH, right, which is X, subtracted from 14 gives us 8.72. So we know that I figured it was in the high eights. The actual pH at equivalence is 8.72. So we're going to talk about indicators in just a minute. We can pick our indicators based upon when they change colors. Come on. There we go. And if we do titrations for different acids, that's what we're showing here. Let's see. This one in the middle is Ka 10 to the minus 4, somewhere between 10 to the minus 4 and 10 to the minus 6, right in here. It's going to be right along in there is where our acetic acid is going to reach equivalence right there. But if the Ka is a lot lower, then the equivalence point is going to be at a lower pH. And if it's much above, it's going to be at a higher pH. And we can use that information also for manufacturing buffers at different pHs because you want to be in the middle of this gentle slope when you're calculating, when you're deciding on which one to use for a buffer. Okay, so I don't think there's anything to talk about there. This particular graph shows a pH curve for the polyprotic acid H3PO4, phosphoric acid. Notice that we have 3 equivalence points and 3 buffer zones. The first buffer zone for that first proton occurs at 2.16, right? That's the pKa for the first proton. The second proton occurs at 7.21, and the third occurs at 12.32. So with phosphoric acid, we can pick which one of those we want for our buffer zone. Right? We've got a choice. And that's why phosphate buffers, when they say phosphate buffers, they're not kidding. They're using phosphate because it's flexible. You can adjust the pH into any one of those buffer regions. Okay, we've identified an equivalence point here. The end point is referring to when the titration is over. The titration is over when you're close to the end point, close to the equivalence point, and the end point tells you that your indicator has changed color. So the end point is not always, it's rarely exactly on the equivalence point, but it's very close. And since this is a very steep slope, it doesn't have to be right on it because This is changing very fast, but this isn't changing much at all. Like this position down here changes just a hair and it goes way up here. So if the color changes way up here, we're close enough to the equivalence point that it doesn't matter. Right? And it's all based upon that steep slope right there. Okay. So here's an example, our phenolphthalein that we've used before. All right. Then we do the molar mass of citric acid last year or last semester. Yeah. We use phenolphthalein for that one. And this just shows you that it's clear when it's acidic and pink when it's basic. The one point to draw from this, the first point is that pH indicators, buffer indicators, are undergoing a chemical reaction themselves at the same time as your main reaction. But we use such a small amount, it doesn't significantly impact this reaction. I mean, it doesn't steal a lot of hydrogens from the main reaction to make its reaction go. So we find that the pKa for and the pH at which this buffer changes color is 9.4, right? We had 8.6 something or 8.7 for acetic acid, 9.4. This is like 8.7, and 9.4 would be up here somewhere, right? We're close enough. And that's just the molecular change. Right. The protonated one is on the left, the deprotonated one is on the right. And the deprotonated one has lost its proteins because of the base, which turns it pink. And the one on the left has its hydrogen, which makes it colorless. Colorless to us. I mean, it has an absorbance, probably in the ultraviolet, but we can't see it. And that's all right. We don't need to see it. Okay. Let's see. Oh, here we get into some physiology. So, how sensitive is the human eye to changes in color? Not very, right? It's plus or minus 1 pKa from the equivalence point of your reaction will get you in a region where your eyes can detect the color change. So if your pH, well, if the pKa for your indicator is 9.4, 9.5, then you should be able to use it for a reaction where the equivalence point occurs between 8.4 and 10.4. That's the rule of thumb. I find it's a lot easier to use a chart, right? It shows you color changes for the different indicators, right? And let's see, phenolphthalein is, where's my thing? Phenolphthalein is right here, right here. So it shows that from pink to red, we're between 8 and 9, 8 and 10. So if you needed one for a more acidic equivalence point, you would move up here to something like bromophenol blue or methyl red, something like that. And there are combination indicators too. Right? There's one called a universal indicator. And with that one, you need a pH chart. So you stick your paper into your solution and you compare it to the chart to see what the pH is. And it's a combination of several of these. You have to pick them so that the color changes don't interfere with one another or don't mimic one another. But it can be done. It has been done.